IR spectroscopy. Spectroscopy is the study of interaction of matter with electromagnetic radiation. There are different types of electromagnetic radiation, each associated with a particular energy range. Here are the different types of electromagnetic radiation, and all of these together is called as the electromagnetic spectrum. The radio waves are the ones which have the lowest energy, and it is used in radio and television communication, and also in digital imaging and wireless linkages to computers. This is the same energy that is used for NMR spectroscopy and also MRI, which is one of the medical applications. And the next higher in energy is the microwaves, and we already know that we use this for cooking. One of the greatest advantages of this, we use this for cooking. And next one is the infrared radiation. This is generally the radiation that we experience as heat. The visible region is what we actually see of the electromagnetic spectrum. The next one that is higher in energy is the component of sunlight called as the ultraviolet radiation. It generally causes sunburns, and repeated exposure of this ultraviolet radiation is going to give skin cancer. X-rays. Low dose X-rays are used in several medical applications, and one of the most important major application of the low dose X-rays is to examine the internal structure of organisms. Whereas high dose X-rays can be harmful to organisms. And the next one is the gamma rays. Gamma rays are generally emitted by the nuclei of certain radioactive elements. Because of the very high energy, they can severely damage biological systems. The last one is the cosmic rays. These are discharged by the sun, and they are the ones which have the highest energy in the electromagnetic spectrum. You look into the electromagnetic spectrum, you can clearly see that as you go from right to left, from radio waves to cosmic rays, the energy of the radiation increases, and therefore the frequency also increases. But as you go in the opposite direction, the energy and frequency is going to decrease while the wavelength is going to increase. So high energy means high frequency but shorter wavelengths, and in the same way, low energy, low frequency is associated with longer wavelengths. The electromagnetic radiation has wave-like properties and can be characterized by its frequency and wavelength. Here is the relationship between energy, frequency, and wavelength. E equals h nu, where h is going to represent Planck's constant and nu is going to represent frequency. Frequency can also be related to lambda using this equation. H nu equals hc by lambda, where c is going to represent the speed of light, that is equivalent to 3.0 times 10 to the power of 10 centimeter per second, and lambda is the wavelength. Let's take a look into the components of wave. The highest point in the wave is called as the wave crest. So these points right here are called as the wave crests. And the lowest point in the wave is called as the wave trough. And the distance between the wave crest and the wave trough is called as the height of the wave, and it's called as the amplitude. The wavelength can be defined as the distance between two consecutive wave crests. So this distance right here is called as wavelength. And frequency is defined as the number of wave crests that passes by a given point in 1 second. Instead of frequency, we can use wave number. Wave number is denoted by this symbol, nu bar, which is basically the number of waves that is produced in 1 centimeter. So in the case of frequency, it's the number of wave crests that is formed in 1 second passing through a point, but here it's the number of waves that is produced in 1 centimeter. And we can relate the wave number with the frequency using this equation. Let's see how we get this. So from here, we know that nu equals c by lambda. If we cancel the h together, it's going to be nu equals c by lambda, right? So now lambda equals C by nu. So nu bar from this equation, it's equivalent to 1 by lambda. When you substitute the value for lambda here, you'll be able to get nu by C. So that is equivalent to 1 by C by nu, and then this is denominator of a denominator, and when you do that, it's going to become nu by C. So wave number is directly proportional to frequency, but it is inversely proportional to wavelength. So when you say high energy radiation, it is associated with high frequency also and large wave numbers, but short wavelengths.